June 29th, 2022. It was a Wednesday. Most people on Earth woke up, made coffee, checked their phones, and went about the business of living. Nothing felt different. The sun rose on schedule. Clocks ticked forward as they always had. Somewhere in the background, satellites hummed in orbit. Atomic clocks counted their billions of vibrations per second, and the entire apparatus of global civilization ran exactly as it was designed to run. Except the planet beneath all of it had just done something it had never done in the 53 years since humans began measuring Earth's rotation with atomic precision. It finished one full rotation in less time than ever recorded. The day was 1.59 milliseconds shorter than normal. Now, stop. Before you move on, before your brain files that away as a scientific curiosity too small to matter, I want you to sit with what that number actually means. Not in human terms, not in terms of whether you felt it or noticed it, or whether it changed your Tuesday. In planetary terms, in the terms of a system that has been spinning for 4.5 billion years, a planet that old does not suddenly change its behavior without a reason. And when that planet, your planet, the only one you have ever stood on, breaks the record not once, but repeatedly, year after year, posting the shortest days ever measured across 2020, 2021, and 2022 in succession, the question is no longer whether something unusual is happening. The question is, what is driving it? And what does it mean for everything built on top of it? That is what this documentary is about, and the answer runs 1,800 miles straight down, through solid rock, through flowing magma, through pressures that would crush any known material to powder, into a place no human instrument has ever physically reached. A churning ocean of liquid iron, a solid sphere at the center of everything, and a set of changes happening simultaneously across multiple layers of the planet that researchers are only now beginning to understand as a connected system. But before we go down, we need to understand why time itself, not metaphorically, not philosophically, but literally, mechanically, in terms of atomic clocks and satellite signals and internet infrastructure, is starting to drift, and why that drift threatens to break something most people do not even know exists. There is a scenario that engineers at some of the largest technology companies on Earth have described as potentially catastrophic. It does not involve a meteor. It does not involve a supervolcano. It involves 1 second. Specifically, the possibility of removing 1 second from the global clock, a negative leap second. If that happens, if the clocks that run the internet, the satellites, the financial markets, and the power grid are forced to subtract 1 second from reality, the consequences could cascade in ways that make the 2012 Reddit crash look like a minor inconvenience. And the planet spinning faster is exactly the thing that might force that to happen. This is the story of an Earth that is behaving differently than it ever has in recorded history. A story that involves the magnetic field weakening over the South Atlantic, the inner core potentially spinning in the wrong direction, ice sheets redistributing the mass of the planet in real time, and a global timekeeping system that was never designed for a world moving at this speed. It is a story that most people do not know is being told. But it is being told right now. In the rotation of the planet you are standing on. In the churning of iron 2,000 miles below your feet. In the data streaming from satellites measuring a gravitational field that is quietly, measurably, undeniably changing. We begin at the surface, with time, with a clock, with the question of why a millisecond, a fraction of a blink, is the number that might change everything. Why Earth has always been slowing down, and why it stopped. There is a force acting on this planet that has been slowing it down for hundreds of millions of years. It is not dramatic. It does not announce itself. You cannot feel it, hear it, or see its effects in any single lifetime. But it is real, it is relentless, and it has been reshaping the very structure of time since before complex life existed on Earth. That force is the Moon. Here is how it works. The Moon's gravity pulls at Earth's oceans. As the planet rotates, that gravitational pull creates tidal bulges, massive swells of water that are dragged slightly ahead of the point on Earth directly facing the Moon. The ocean does not want to be in the wrong position. Friction between that displaced water and the rotating seafloor beneath it acts as a brake. Every day, every tide, every cycle of pull and release bleeds a tiny fraction of rotational energy from the planet. Over millions of years, this adds up to something profound. 400 million years ago, a year contained more than 400 days. We know this not from records. Nothing was writing things down, but from the growth rings of ancient coral. Coral grows in daily increments, leaving faint lines that scientists can count like tree rings. Fossil coral from the Devonian period shows roughly 410 growth rings per year. Since the length of a year is fixed, determined by Earth's orbit around the Sun, more days per year means shorter days. The planet was spinning faster. 600 million years ago. Based on tidal rhythmite records, layers of sediment deposited by ancient tides in sequences that preserve the count of tidal cycles, Earth's day was approximately 21 to 22 hours long. The direction of travel was clear. The planet was decelerating, slowly, imperceptibly, on a geological clock, but absolutely and in one direction. More tidal drag, more energy transferred from rotation to the Moon's orbit, more lengthening of the day. This is the baseline, the expected behavior, the trajectory that 4.5 billion years of physics established as the norm. Then, around 2016, something stopped it. Not reversed it, not dramatically, not instantly. But the trend line that had been pointing toward slower and slower rotation began to bend. The average length of a day, which had been tracking within a tight range for decades, started showing something that the instruments had not seen before. The days were getting shorter, slightly, consistently, in a direction opposite to what tidal friction predicted. The International Earth Rotation and Reference System Service, the organization based in Paris that coordinates global monitoring of Earth's rotation, noticed. They ran the checks. They compared data from atomic clock networks across multiple continents. They looked for instrument error, for calibration drift, for anything that might explain a signal this unexpected. The instruments were fine. The signal was real. And here is the detail that made researchers stop mid-sentence in conference rooms and late-night data reviews. When scientists subtracted every known contributing factor from the rotation data, tidal friction, seasonal atmospheric shifts, ocean loading, the gravitational influence of the moon, a residual acceleration remained. Something beyond the catalogued causes was pushing the planet forward. They had a measurement. They did not yet have a complete explanation. The candidates were many. Ice loss from Greenland and Antarctica, redistributing planetary mass like a spinning skater pulling her arms inward. Changes in atmospheric circulation driven by a warming Arctic. Fluctuations in ocean current patterns. And, most unsettling of all, something happening in the liquid iron ocean that surrounds Earth's solid core. 1,800 miles beneath your feet. Each of these forces is real. Each is measurable. The question of which one is dominant, how they interact, and what their combined effect means for a planet that has been decelerating for geological ages, that question is still being answered. But to understand what is happening, you first need to understand the instrument that caught it. Because the story of how humans learned to measure a millisecond is itself one of the stranger chapters in the history of science. Before 1955, the most precise clocks on Earth lost or gained roughly 1 second every 300 years. By daily life standards, extraordinary. By the standards of planetary science, measuring a planet that fluctuates by fractions of a millisecond, nowhere near precise enough. Then physicists built the first atomic clock. The principle is deceptively simple. Atoms do not lie. Every atom of the same element, anywhere in the universe, vibrates at exactly the same frequency. Cesium-133 atoms, the type used in the most precise modern timekeepers, oscillate 9,192,631,770 times per second. Every single time. Without exception, without drift, without caring what time zone you are in, what the weather is, or whether the planet is spinning slightly faster than usual. That frequency became the new definition of a second. Not a fraction of Earth's orbit, not a pendulum swing, not a mechanical wheel. The vibration of a single type of atom, counted 9 billion times over. The result was a clock so accurate it would not gain or lose a single second across 300 million years. With that level of precision suddenly available, scientists could do something they had never done before. They could measure the planet against an absolute standard. And what they found was unsettling from the beginning. Earth's rotation was messy. It fluctuated constantly. It sped up in northern hemisphere winter as atmospheric mass shifted toward the poles. It slowed in summer. Earthquakes made tiny adjustments. Major storms applied measurable pressure. El Niño events, shifts in ocean circulation, even large accumulations of snow at high latitudes, all left faint signatures in the rotation data. This variability was managed. Leap seconds were invented in 1972 to patch the gap between atomic time and Earth time. Whenever the two drifted more than 0.9 seconds apart, 1 extra second was inserted into the official clock. 23:59:60 before midnight. 27 times since 1972. That patch was applied. The system held. Then Earth started speeding up. and for the first time in the history of the system, the discussion shifted to the unthinkable, not adding a second, but removing one, a negative leap second, clocks jumping from 23:59:58 directly to midnight, 1 second that simply would not exist. Engineers at Meta, Google, Amazon, and Microsoft have independently studied what that would do to global digital infrastructure. The word they have used, on record, is devastating. And the planet spinning faster is the reason that word is now on the table. 1,800 miles down, where the planet's engine lives. If you could drill straight down through the ground beneath your feet, through the crust, through the upper mantle, through hundreds of miles of increasingly dense and hot rock, past the point where the pressure becomes so extreme that minerals transform into configurations that do not exist anywhere near the surface, you would eventually reach a boundary. It begins approximately 1,800 miles down. Beyond that boundary, the rock stops being rock. The temperature is roughly 9,000 degrees Fahrenheit, comparable to the outer surface of the Sun. The pressure is more than 1,000,000 times atmospheric pressure at the surface. And in those conditions, iron and nickel behave differently than any material you have ever encountered. They flow, not like water, not like lava, like a liquid metal in a state so compressed and energized that it moves in massive, planet-spanning currents. This is Earth's outer core, a churning ocean of liquid iron extending from 1,800 miles down to approximately 3,200 miles below the surface. An ocean larger than Mars. An ocean you will never see, never directly measure, never send any instrument into. An ocean that has been there since the planet formed, and that generates the invisible force field that makes life on Earth possible. Here is the mechanism. As this liquid iron flows, driven by the temperature difference between the cooler base of the mantle above and the intense heat of the solid inner core below, it carries electrical charge. Flowing electrical charge generates a magnetic field. That magnetic field, generated through a process called the geodynamo, extends outward from the core, through the mantle, through the crust, and out into space. The result is Earth's magnetosphere, the protective bubble that deflects the solar wind, the stream of charged particles constantly emanating from the Sun. Without it, those particles would strip away the atmosphere over millions of years, scorching the surface and making liquid water impossible. Mars lost its magnetic field billions of years ago. Look what happened to Mars. The liquid outer core is, in a very direct sense, why Earth is habitable. But it does more than generate the magnetic field. It physically interacts with the rotation of the solid planet above it. The outer core does not rotate at exactly the same rate as the mantle and crust. There is coupling between them, transmitted through pressure and electromagnetic forces, but the core has rotational independence. When the massive convective currents inside the core shift, when columns of rising and sinking iron change their flow patterns, they exert torque on the layer above them. That torque shows up in the rotation data. Think of it this way. Imagine a jar of honey with a marble suspended inside it. If you rotate the jar, the honey carries the marble along, but not perfectly, not instantly. There is drag, there is lag, and the marble's motion influences the motion of the honey surrounding it. Scale that up by a factor of several trillion. Replace the honey with liquid iron at 9,000 degrees, and replace the marble with a solid iron sphere the size of the moon. And you have a rough intuition for the relationship between Earth's outer and inner cores. Geophysicists studying the correlation between changes in Earth's magnetic field and changes in Earth's rotation have found a consistent pattern. When the field fluctuates in certain ways, the rotation tends to change. The connection is not perfectly understood. The precise mechanisms are still being debated in journals and conferences, but the correlation is strong enough that core dynamics are now treated as a primary driver of decade-scale rotation variations. The acceleration that began around 2016 coincides with changes in the outer core's circulation pattern detected in satellite magnetic data. The timing is not coincidental. And here is where the story gets stranger. Because the outer core does not move in isolation. It wraps around something at the very center of the planet, something solid, something that has its own rotation rate, its own angular momentum, and its own relationship with the layers above and below it. Something that may have recently done something no one expected. At the absolute center of Earth, approximately 3,600 miles beneath your feet, there is a sphere of solid iron, roughly as wide as the moon. It exists in a state that should not be physically possible. The temperature there is approximately 9,000 to 11,000 degrees Fahrenheit, comparable to or exceeding the surface of the sun. At that temperature, iron should be liquid. Iron wants to be liquid. It is not liquid. It is solid. And it is solid precisely because of the pressure. The weight of the entire planet pressing inward. The mantle, the outer core. Every mountain and ocean and layer of rock above it creates pressures exceeding 3 million times the atmospheric pressure at the surface. That pressure forces the iron into a crystalline structure so tightly packed that heat alone cannot shake it apart. The inner core floats inside the liquid outer core the way a ball bearing floats in oil. It is not connected to the mantle or crust by any rigid material. The liquid iron surrounding it is the only medium through which forces are transmitted between the innermost sphere and everything above it. This means the inner core can rotate independently. For decades, geophysicists suspected it did. Proving it required an unusual source of evidence: earthquakes. When a major earthquake strikes, it sends seismic waves radiating outward in all directions, including straight down through the core and up the other side. Researchers at seismograph stations positioned around the globe record those waves and use their travel times to map the interior. Different materials transmit seismic waves at different speeds, and the inner core, with its iron crystal structure, aligned in a particular orientation, transmits waves slightly faster along certain paths than others. By comparing seismic recordings of similar earthquakes over decades, scientists found that the travel times were changing. Waves that passed through the inner core were arriving at slightly different times than they had a generation earlier. The best explanation was that the inner core was rotating, slowly turning relative to the surface. changing the orientation of its crystal structure relative to the paths the waves were traveling. For years, the consensus was that the inner core rotated slightly faster than the mantle above it, a phenomenon called superrotation. Then, in 2023, a study published in the journal Nature Geoscience drew a different conclusion from a longer data set. The inner core had slowed down. It had matched the surface around 2009. Then it had slowed further. And by the researchers' analysis, drawing on decades of seismic data from earthquakes recorded at the same stations, it appeared to have reversed. The innermost sphere of Earth, the solid iron heart of the planet, was now rotating slightly in the opposite direction relative to everything surrounding it. Read that again. The center of the Earth, spinning backward. The forces involved are enormous. The angular momentum of the inner core is not a negligible quantity. Its change in rotation couples through the outer core, through the mantle, through the crust. Angular momentum moving upward through those layers is angular momentum being added to the rotation of the surface. It is like a figure skater throwing their arms outward to slow down, except in reverse, where the energy travels from the innermost layer outward, and the surface speeds up as a result. The timeline fits. The inner core's apparent deceleration in the late 2000s and early 2010s aligns, with a lag appropriate to the transfer time scales, with the surface acceleration that became measurable starting around 2016. That lag is itself scientifically significant. It suggests that information from the center of the planet takes years to decades to propagate upward through the layers, which means that whatever is happening at the core right now, we will not feel its full surface expression for years yet. We are receiving a signal from 3,600 miles down, and we are still learning how to read it. What happened between 2009 and now? Science rarely announces its most important discoveries with fanfare. More often, they emerge from years of careful, unglamorous data comparison, from researchers noticing that a number which should be consistent is not consistent, that a pattern which should repeat is repeating differently, that something buried in decades of measurements is not what the models predicted. The discovery of the inner core's behavioral change was exactly that kind of emergence. For most of the second half of the 20th century, seismologists tracking the inner core's rotation were watching for a very specific signal: the superrotation. The theory, developed through the 1990s and confirmed by multiple independent research groups using different data sets, held that the inner core was rotating slightly faster than the rest of the planet, completing its revolution perhaps about a degree per year faster than the mantle and crust above it. This was not controversial. It was consistent with models of how the core should behave under the electromagnetic forces generated by the outer core's circulation and the gravitational influences of the overlying mantle. The physics made sense. The data agreed. The inner core was spinning faster than the surface. End of story. Except the story was not ending. It was turning. The dataset that changed everything was assembled over decades using what seismologists call repeating earthquakes, events that occur at the same location with the same fault geometry multiple times. Because these earthquakes send nearly identical waves through the Earth on each occurrence, the only thing that should cause their seismic signatures at distant stations to differ is a change in what those waves passed through. A change in the interior. When researchers Yi Yang and Xiaodong Song at Peking University assembled this data set, drawing on recordings from seismograph stations distributed across the globe, covering events from the 1960s through the early 2020s, they found something that did not fit the super-rotation story. The inner core had not continued accelerating relative to the surface. It had slowed down. It had matched the surface rotation approximately between 2009 and 2011. And then it had continued decelerating, rotating slightly more slowly than the mantle above it. In 2023, their analysis was published in Nature Geoscience. The interpretation: the inner core had reversed its rotation relative to the surface. Where it had once been spinning faster, it was now spinning slower. The oscillation from superrotation to matched rotation to subrotation appeared to have a cycle of several decades. The scientific community's response was exactly what you would expect from a field that values rigor above novelty. Scrutiny. Hard, sustained, methodical scrutiny. Critics pointed out that the inner core's surface is not perfectly smooth. It has topographic features, ridges and valleys of iron crystal that could scatter seismic waves differently over time without requiring rotation. Changes in the outer core above could also affect wave travel times. The data, while compelling, was not unambiguous. Alternative interpretations existed. Both sides acknowledged that the seismic evidence was real. What they disagreed on was the interpretation. Here is what both sides agree on, and this is the thing that matters most. Something changed inside the planet. The inner core's behavior in the 21st century is measurably different from its behavior in the 20th century. Whether that change represents a full reversal of rotation direction or some other structural shift in the core's dynamics, the effect is real and it is propagating upward. The mechanism connects to the surface through angular momentum conservation. When the inner core decelerates, its angular momentum does not disappear. It transfers through electromagnetic and gravitational coupling to the outer core. The outer core transfers it to the mantle. The mantle transfers it to the crust. Angular momentum moving upward through those layers is angular momentum being added to the rotation of the surface. The timeline is consistent. The inner core's apparent behavioral change beginning around 2009 to 2010 aligns, with a lag of years to a decade, appropriate to the coupling time scales, with the surface acceleration that became clearly measurable around 2016. This is not coincidence. This is signal propagation through a layered system. But the core is only one part of what is happening, because at the same time, the core was shifting its rotational behavior. Something was happening at the surface of the planet. Something dramatic. Something accelerating. Something that was reshaping the planet's mass distribution in real time. And it was coming from the poles. The Greenland ice sheet covers 660,000 square miles of the North Atlantic's largest island under ice that in places reaches 2 miles thick. The West Antarctic ice sheet contains enough water to raise global sea levels by roughly 11 feet if it fully melted. These are not abstractions. They are masses of ice so large that their gravity measurably distorts the ocean around them, pulling water toward them the way a massive object bends space. And they are melting, not gradually in a way that models from 20 years ago predicted. Faster, substantially faster. Greenland is now losing approximately 280 billion metric tons of ice per year. Antarctica is losing roughly 150 billion metric tons per year. These are numbers large enough to detect from space, not in terms of visible melting, but in terms of the gravitational field. The Grace and Gracefo satellite missions, 2 spacecraft flying in formation, tracking the distance between them to within a fraction of a micrometer, measure tiny variations in Earth's gravitational field by detecting how mass shifts on the surface pull them closer together or push them further apart. When ice melts, the gravitational signature changes. The satellites see it. The picture they have returned is striking. The poles are losing mass. The ocean basins at lower latitudes are gaining it. The planet's distribution of weight is changing in real time. And when the weight of a spinning object shifts, the spin changes with it. This is the same physics that makes a figure skater speed up when they pull their arms in. The skater is conserving angular momentum. As their mass moves closer to their rotation axis, their rotation rate increases to keep the total momentum constant. When their mass moves away from the axis, they slow down. Ice at the poles sits close to Earth's rotation axis. When that ice melts and the water flows into the ocean at lower latitudes, mass moves away from the rotation axis. The planet's moment of inertia increases, and with angular momentum conserved, the rotation rate should decrease. In the long run, it will. But in the transition, right now, in the decades we are living through, the redistribution is happening simultaneously in multiple regions at different rates with different rotational signatures. The net effect oscillates even as its long-term average moves in one direction. And at the same time, the poles are shifting mass. The core is shifting angular momentum. And the atmosphere is redistributing its own mass as the jet stream changes behavior. And the oceans are reorganizing their circulation all at once. All in the same decade, all in a direction that has compounded into the fastest rotation rate recorded in 50 years of precise measurement. This is not a coincidence. This is a coupled system entering a new regime. How melting ice changes the speed of a planet. There is a demonstration in physics classrooms that never fails to make people gasp. It requires only a rotating stool and 2 heavy weights, 1 in each hand, arms extended. The stool spins slowly. Then the person pulls their arms inward, bringing the weights close to their body. The stool speeds up, dramatically, instantly, without anyone pushing. No external force was applied. No energy was added from outside the system. The person simply moved mass closer to the rotation axis. And to conserve angular momentum, one of the most fundamental quantities in physics, the rotation rate had to increase. Earth works by exactly the same principle. For most of the last 20,000 years, the planet has been redistributing mass in a specific direction, away from the poles toward the equator. The great ice sheets of the last glacial maximum, Kilometers of ice covering North America, Northern Europe, and Antarctica began their retreat roughly 18,000 years ago. As they melted, the water entered the oceans and spread across lower latitudes, mass moving away from the rotation axis, moment of inertia increasing, rotation slowing slightly on geological timescales. This process, called post-glacial rebound, is still happening. The crust beneath where those ancient ice sheets sat is still rising, freed from the weight of ice it bore for tens of thousands of years. Scandinavia is rising by roughly 4 millimeters per year. Parts of Canada are still lifting. The adjustment will continue for thousands of years more. For most of the Holocene, the 11,000 years of relative stability in which human civilization developed, this process operated as a gentle, persistent brake on rotation. The planet was gradually, almost imperceptibly, slowing down in response to deglaciation. What is different now is the rate. The Greenland ice sheet and the West Antarctic ice sheet are not melting at the gentle pace of post-glacial retreat. They are losing mass at rates that have accelerated sharply since the 1990s, and that acceleration is itself accelerating. Models from the early 2000s underestimated how quickly the ice sheets would respond to warming by significant margins. The actual data has outpaced successive generations of projections. Greenland alone is now losing roughly 280 billion metric tons of ice per year. Put differently, every year, enough water to fill Lake Erie roughly 4 times over is leaving the ice sheet and entering the global ocean. From a rotation standpoint, the short-term and long-term effects are different, and this distinction is crucial to understanding what we are seeing right now. The long-term effect of ice loss is to move mass to lower latitudes, increasing Earth's moment of inertia and eventually slowing the rotation. That is the physics textbook answer, and it is correct on timescales of centuries. But we are not on those timescales. We are in the transition. And during the transition, the redistribution is happening simultaneously in multiple regions at different rates with different rotational signatures. The net rotational effect at any given moment is the sum of contributions from Greenland melting faster in summer, Antarctic glaciers calving throughout the year, monsoon cycles moving water between basins, and El Niño events reorganizing oceanic mass. This sum oscillates, it fluctuates seasonally, it varies interannually, and beneath those fluctuations, its long-term average is moving toward slower rotation, but not yet. Not in the short term we are currently measuring. There is another effect that adds a further complication. When ice melts, the water does not simply pour uniformly into the global ocean and settle evenly. It cannot. The ocean is not a static bowl. It is a rotating, three-dimensional fluid system wrapped around an irregularly shaped mass with uneven internal density. The planet's rotation itself influences how water distributes across ocean basins. And ice sheets, while they exist, have their own gravity. The Greenland ice sheet is massive enough that its gravitational attraction pulls ocean water toward it. The ocean surface near Greenland is actually pulled upward, slightly higher than it would be if Greenland were flat rock, by the ice sheet's gravity. When the ice melts, that gravitational attraction weakens. The water that was pulled toward Greenland sloshes away, southward toward lower latitudes. Coastlines near Greenland experience a small sea level drop as Greenland loses ice. Coastlines in the tropics and southern hemisphere experience a disproportionately large rise. This gravitational fingerprint of ice loss is measurable. It has been measured. Different ice sheets leave different fingerprints based on their location and the direction their meltwater moves. And those fingerprints have different implications for the rotation depending on where the mass ends up relative to the rotation axis. The GRACE satellite mission detected all of this. Year after year, it mapped the gravitational field changing in real time. The data showed the poles losing mass and the ocean basins at lower latitudes gaining it. The planet's moment of inertia was shifting. The rotation axis itself was physically moving. That last part deserves its own attention. The geographic North Pole, the point on the surface directly above Earth's rotation axis, is not fixed. It wanders. It has always wandered, driven by the mass distribution of the planet. For most of the 20th century, it drifted slowly toward northern Canada, driven primarily by post-glacial rebound in the Hudson Bay region. Around the year 2000, and the direction of drift changed. The pole turned eastward toward Greenland. The rate of drift increased from a few centimeters per year to roughly 17 centimeters per year over the following 2 decades. When researchers analyzed the cause of this directional shift, the data pointed clearly to accelerated Greenland ice loss. The mass leaving Greenland's ice sheet was physically pulling the rotation axis in a new direction. Western Antarctic ice loss contributed as well, adding to the net eastward trend. The actual geographic pole, the invisible point around which everything rotates, is now located measurably differently from where it was when you were born. This is not a dramatic shift in the planet's orientation. It would not change where you see the North Star on any human time scale. But at the precision required by satellite navigation systems, geodetic surveys, and time transfer infrastructure, it matters enormously. Every system that uses the precise location of Earth's rotation axis in its calculations must be updated to account for the drift. Those updates have been coming faster in recent years, and the rate of ice loss is not slowing. It is accelerating. The planet is literally moving its weight around as we watch, and everything built to assume the weight stays still is quietly, steadily being tested. The Timekeeper's War and the second that could break the internet. In 1972, the world quietly agreed on a patch. The problem was not dramatic. There were no headlines, no emergency sessions, no sense of crisis. The problem was simply this: atomic clocks, anchored to the vibration of cesium atoms, were now the gold standard for timekeeping. They were precise beyond anything previously possible, and they were anchored to physics, to the behavior of matter, not to the rotation of a planet. The planet, it turned out, was an unreliable timekeeper. Its rotation fluctuated. It had been gradually slowing for geological ages due to tidal drag. And if nothing was done, atomic time and Earth time would drift further and further apart with every passing decade. Not tomorrow, not next year, but across centuries, the drift would become undeniable. Eventually, noon on the clock would arrive while the sky still showed late morning. The solution was the leap second. Once or twice a year, When the gap between atomic time and Earth time grew large enough, international timekeeping authorities would add a single extra second to the official clock. Clocks around the world would tick from 23:59:59 to 23:59:60 before rolling over to midnight. One extra heartbeat inserted into global time. 27 times since 1972, that heartbeat was added. Not one was ever removed. The planet was always slowing, which meant atomic clocks always ran ahead, which meant the fix was always to add time. Now the planet is speeding up. Atomic clocks are falling behind Earth time. The gap is accumulating in the wrong direction. And for the first time in the history of the leap second system, the discussion has shifted from adding seconds to something that has never been done: removing one. A negative leap second, clocks jumping from 23:59:58 directly to midnight, 23:59:59, would simply not exist. Engineers at Meta, the company that operates Facebook and Instagram and relies on precise time synchronization across billions of devices worldwide, published a technical paper assessing the consequences. Their language was unusually direct. They described the negative leap second as an event with a devastating effect on software relying on timers or schedulers. Their recommendation was not to implement one at all, but rather to spread any necessary correction across a longer period, smearing the adjustment over hours rather than applying it in a single jump. Google has independently developed a similar approach, called a leap smear. Microsoft has its own variant. Amazon operates yet another. None of them are identical, which means that in the event of a negative leap second, the largest technology organizations on Earth would be running subtly different versions of time simultaneously, and any system that compares timestamps across platforms would encounter ambiguity. Let me make this concrete. The Internet runs on a protocol called the Network Time Protocol, NTP, which continuously synchronizes clocks across billions of connected devices. It was designed to handle time moving forward. It was never designed to handle time moving backward. When a system's internal clock suddenly reads 1 second earlier than it did a moment before, processes scheduled to run at a specific timestamp can trigger twice. Logs that record events in chronological order can record new events as if they happened before old ones. Security certificates that verify identity using timestamp matching can fail. Distributed databases that use timestamps to resolve conflicting updates can choose the wrong version of a record. In a social media context, that means a post might be duplicated, or a comment might appear before the comment it was responding to. Cosmetic, fixable, embarrassing, but not catastrophic. In a financial context, it means something different. Stock exchanges in New York, London, Tokyo, and Frankfurt execute millions of trades per second. Each transaction carries a timestamp accurate to the microsecond. Those timestamps are synchronized to coordinated universal time, which is itself anchored to atomic clocks. A desynchronized planet creates a desynchronized timestamp. High-frequency trading systems, the automated programs that execute thousands of transactions per second based on market microstructure, depend on the sequence of timestamps to determine which order came first. If two exchanges' clocks jump backward at slightly different moments, the sequence of trades becomes ambiguous. Transactions that appeared settled become disputed. Trades placed after the subtracted second might be logged as occurring before trades placed before it. Regulatory bodies in the United States and the European Union require financial institutions to keep records accurate to the microsecond in some jurisdictions. A 1-second reversal does not just create confusion. It creates legal liability. And the volume of transaction records that would require manual review after a negative leap second has been modeled by the Bank for International Settlements. The number they arrived at was considered significant enough to be classified. Power grids present a different version of the same problem. Alternating current flows at a fixed frequency, either 50 or 60 cycles per second, depending on the country. Grid operators synchronize their systems to universal time to balance electrical load across regions spanning thousands of miles. When time drifts, load balancing drifts with it. A sudden discontinuity, 1 second backward, creates a window where the coordination signal between grid sections breaks down. In most cases, backup systems compensate within minutes. But the industry has a term for what happens in that gap: a synchronization event. And synchronization events, even brief ones, are the precursor to the kind of cascading failures that can bring down large sections of a grid. Aviation adds yet another layer. Air traffic control systems depend on synchronized timestamps to track aircraft positions and resolve conflicts between flight paths. When controllers at different facilities are working from clocks that disagree, even briefly, the margin built into separation standards gets consumed by the ambiguity. Modern instrument approach procedures, the ones that guide aircraft to within feet of a runway in zero visibility, use satellite positioning with tolerances measured in meters laterally and feet vertically. Those systems depend on Earth rotating predictably and the clocks synchronized to that rotation behaving consistently. Hospitals are perhaps the most underappreciated example. Modern hospitals are dense with time-critical systems. Medication dispensing systems log timestamps on every dose. Operating room equipment, particularly anesthesia delivery and patient monitoring, records data against synchronized timestamps that form the legal medical record. Linear accelerators used in cancer treatment use precise timing to coordinate radiation beam delivery with patient breathing cycles. A 1-second discontinuity in the timekeeping system does not just create a data anomaly. It creates a gap in the medical record that triggers automatic safety alerts, and in some cases, automatic system shutdowns pending manual verification. In 2022, an international standards body voted to eliminate the leap second entirely by 2035, allowing atomic time and Earth time to diverge without correction until a different mechanism can be developed. The decision sounded like a solution. It was actually a deferral. The gap would still grow. The correction would still eventually be needed. The question of what form it would take was simply postponed. And the planet, heedless of policy decisions, kept accelerating. In 2034, in the scenario that engineers at the major technology companies have internally modeled, the accumulated drift forces an emergency meeting of international timekeeping authorities. The models show that waiting for the new mechanism is no longer acceptable. A negative leap second is scheduled. The announcement goes out 6 months in advance. Engineering teams at every major technology company, power utility, and financial institution begin preparation. Most implement time smearing, spreading the correction across a 12-hour window so their systems never experience an abrupt discontinuity. Most, not all. The systems that cannot easily implement smearing include legacy power grid control systems running on software stacks too rigid to accommodate gradual adjustment, banking transaction clearing platforms operating under regulatory requirements that mandate specific timestamp precision, and industrial control systems in manufacturing and chemical processing, where timing is locked to hardware interrupts. At the moment the second is removed, 23:59:58 jumping to midnight, the voices that were synchronized begin to split. Devices that implemented smearing are operating in slightly different versions of time from devices that did not. During the smearing window, a timestamp from one system disagrees with a timestamp from another by up to 1 second. In most applications, this is manageable. In some, it is not. None of this collapses civilization. The planet does not stop. Lights come back on. Transactions eventually reconcile. The episode becomes an engineering case study taught in graduate programs a decade later. But in the months following the adjustment, audit reports identified dozens of incidents in which the timekeeping discontinuity was a contributing factor. The financial system absorbs reconciliation costs measured in billions. 3 grid sections in different countries experience brief outages. Hospital systems in 2 countries initiate manual reviews of approximately 40,000 time-stamped medical records. This is the scenario engineers have been trying to avoid for years, and the planet spinning faster is the reason they cannot avoid discussing it any longer. The patch from 1972 was never designed for a world moving at this speed. And the world is moving faster. There is a region of Earth where the invisible force field that protects life on this planet is, right now, failing. Not catastrophically, not yet, not in a way that is causing immediate harm to the people who live beneath it, but measurably, consistently, and at a rate that is accelerating in ways that concern the scientists who monitor it. The region is called the South Atlantic Anomaly. It is centered roughly over the South Atlantic Ocean and extends across much of South America, covering some of the most populated areas of the Western Hemisphere. Within this region, Earth's magnetic field is significantly weaker than at equivalent latitudes elsewhere on the planet. In the strongest part of the anomaly, the field is roughly 40% weaker than it would be on the opposite side of the Earth. That weakness has a consequence at altitude. Earth's magnetic field deflects charged particles from the Sun, the protons and electrons streaming outward in what is called the solar wind, as well as higher energy cosmic rays arriving from beyond the solar system. In most locations, this deflection begins at a sufficient altitude that satellites in low Earth orbit are well protected. In the South Atlantic Anomaly, the field is so weak at lower altitudes that charged particles penetrate further before being deflected. Satellites passing through this region experience elevated radiation levels that can cause electronic malfunctions. The International Space Station, whose orbit carries it through the anomaly regularly, takes explicit precautions. Crew members are warned. sensitive instruments are powered down or shielded. Astronauts schedule their rest periods to minimize their time in the anomaly. This has been documented since the 1950s. It is not new. What is new is that it is growing. The South Atlantic anomaly has been expanding in area and deepening in its minimum intensity for decades. European Space Agency data from the SWARM satellite constellation, 3 satellites flying in formation to map the global magnetic field with unprecedented resolution, has shown the anomaly growing steadily. The minimum field intensity within the anomaly has declined consistently, and in recent years, the data has shown something new. The anomaly appears to be developing a second minimum, splitting into 2 separate weak spots, each with its own center. A single anomaly becoming 2. The cause is tied directly to what is happening beneath it in the outer core. Under the South Atlantic, there is an unusual structure in the outer core called a low-velocity zone, a region where liquid iron moves differently from the surrounding material. Some researchers believe this zone represents a patch of reversed magnetic polarity, where the local field alignment is opposite to the global dominant direction. In a normal magnetic reversal, the kind that has happened hundreds of times in Earth's history, the entire global field weakens, the poles wander, and eventually the North and South poles exchange positions. The process takes thousands of years. What may be happening in the South Atlantic anomaly is that one of these reversed patches is growing, weakening the field above it from below. The reversed patch is not static. It is growing. The global magnetic field has declined by approximately 9% since measurements began in the early 19th century. 9% in roughly 180 years. On geological time scales, that is an exceptionally fast rate of change. Whether it represents the beginning of a full reversal, an excursion, a temporary fluctuation that will recover, or something else entirely, is not yet determinable from the data. What can be said? The field is behaving differently today than it was 200 years ago. The connection to Earth's rotation runs through the same outer core dynamics that affect the spin. Changes in outer core flow patterns affect the magnetic field. Changes in the magnetic field affect the electromagnetic coupling between the outer core and the mantle. And changes in that coupling affect the transfer of angular momentum between the core and the surface. The South Atlantic anomaly is not just a radiation hazard for satellites. It is a visible symptom of changes happening in the outer core, the same outer core whose dynamics appear to be linked to the surface acceleration. The 2 phenomena share an origin, and if the anomaly's low-velocity zone continues to grow, it will affect both the magnetic field above and the rotational coupling below. The practical consequences of a growing anomaly are already manifesting in satellite operations. Dozens of satellite operators, commercial, scientific, governmental, have developed specific protocols for managing their spacecraft when they pass through the anomaly. Electronic components that would normally operate continuously must be cycled off and on. Data collection windows must be scheduled around the anomaly's position. Redundant systems must be kept active in regions where they would normally be dormant. The operational cost of the anomaly is not trivial. It represents real engineering constraints, real scheduling limitations, real expenses in satellite operations that did not exist at this scale a generation ago. and the anomaly is growing. The last time Earth's magnetic field weakened significantly on a global scale, something more dramatic followed. Examining the geological record, the preserved magnetic signatures in ancient rock, the layered evidence in seafloor sediments, researchers can identify periods when the field weakened, sometimes dramatically, before recovering without a full reversal. These are called geomagnetic excursions. The best studied example is the Leschamp excursion, approximately 42,000 years ago. During that event, global field intensity dropped dramatically over several centuries to perhaps 5% of its normal strength before recovering over several thousand years. Evidence in cave records, ice cores, and tree rings from that period suggests elevated cosmic ray flux and unusual atmospheric chemistry during the excursion. Some researchers have connected it to periods of accelerated climate change and extinctions of large mammals, though the causal chain remains debated. The point is not that another Leschamp event is imminent. The point is that these events are real. They have happened. They left measurable signatures in the biological and geological record, and the current state of the magnetic field has measurable similarities to conditions that preceded past excursions. The ancient record does not predict the future, but it defines the range of what is possible, and that range is wider than most public discussions of the magnetic field suggest. The instruments are running, the data is coming in, the field continues to weaken, and the outer core beneath the South Atlantic continues to churn in patterns that remain only partially understood. We are watching something happen in real time that we cannot yet fully interpret. But we are watching it more carefully than any generation of humans has ever watched before. There is a library inside the planet. Not books, not symbols, not any record that required a mind to create, but physical information pressed into stone at the moment it formed, mineral alignments frozen in place as lava cooled, chemical signatures crystallized in seafloor sediments, growth rings laid down in coral skeletons 400 million years ago. That can be read today by scientists with the right instruments and the right questions. This library extends back more than 4 billion years. It is incomplete, damaged in places, legible only through methods that took decades to develop. But what it contains about Earth's rotation, its magnetic field, and its behavior during periods of transition is irreplaceable. It is the only record we have of how the planet has navigated moments like the one we may now be entering. Begin with the coral. In the 1960s, paleontologist John Wells at Cornell University proposed something that seemed almost impossibly clever. If corals grow in daily increments, leaving growth rings like trees, then ancient coral should record the number of days in a year at the time it was alive. The orbit of Earth around the Sun has not changed significantly in hundreds of millions of years. A year is still approximately the same length of time. So, if coral from 400 million years ago shows 410 growth rings between annual markers, then 400 million years ago, there were 410 days in a year. More days per year, same year length, means shorter days. The measurements confirmed it. Devonian coral showed approximately 400 to 410 daily growth rings per year. The planet was spinning faster. The days were shorter. Tidal rhythmite records, sequences of fine-grained sediment deposited by tides in ancient tidal flat environments, preserved in places like South Australia and the Yangtze Gorges region of China, extend the record further back. These rhythmites preserve not just daily tidal cycles, but semi-diurnal patterns, monthly cycles, and annual variations that allow reconstruction of the Moon's distance and Earth's rotation rate at the time of deposition, from approximately 620 million years ago, a day of roughly 21 to 22 hours. The Moon was closer. Its tidal breaking was more intense. The deceleration was steeper. From approximately 1.4 billion years ago, rhythmites in Montana suggest a day of roughly 18 hours. The Moon still closer. The tides higher. Why the breaking even stronger. The long-term trend is clear, consistent, and confirmed by independent lines of evidence. Earth has been decelerating for billions of years. The geological record is the long-term baseline against which any short-term departure must be measured. But the record also shows something else. Within that long deceleration, there are variations, periods where the rate of slowing changed, brief episodes where small reversals of the trend occurred. The geological record shows that Earth's rotation is not a simple one-way ratchet. It has fluctuated on timescales from decades to millions of years, driven by the interplay of tidal breaking, core dynamics, and mass redistribution. The paleomagnetic record adds another dimension to this picture. When lava erupts and cools into basalt, tiny magnetic minerals in the rock align themselves to the direction and intensity of Earth's magnetic field at that exact moment. They freeze in place as the rock hardens. The record they carry can survive for hundreds of millions of years without degradation. Using this method, researchers have mapped the history of Earth's magnetic field with remarkable detail going back more than 4 billion years. The picture that emerges is one of perpetual change. The poles have reversed hundreds of times, north becoming south, south becoming north, on an average schedule of roughly every 200 to 300,000 years, though with extraordinary variability. Some reversals are separated by tens of thousands of years, others by tens of millions. The last full reversal, called the Brunhes-Matuyama reversal, occurred approximately 780,000 years ago. By the average statistics of the reversal record, we are overdue. That word requires immediate qualification. Overdue, in this context, means past the average interval. It does not mean the reversal is imminent. The distribution of reversal intervals is so broad, ranging from tens of thousands to tens of millions of years, that being past the mean tells us almost nothing about when the next one will occur. The timing of reversals is not clockwork. It is driven by dynamics in the outer core that we do not yet fully understand. What the geological record of reversals does tell us is that they happen. They have happened repeatedly throughout Earth's history. Life has survived every one of them. Complex life, sophisticated life, diverse life. It has persisted through hundreds of magnetic reversals across 500 million years, but survived is doing some work in that sentence. During a reversal, the field does not flip instantaneously. The transition takes thousands of years. During that transition, the field weakens significantly, potentially dropping to 10 or 20% of its normal strength globally. The protection against charged particles from above is reduced across most of the planet. Increased radiation reaching the surface elevates cancer rates. Satellites and power grid infrastructure suffer intensified damage. Animal navigation systems that depend on magnetic sensing, migratory birds, sea turtles, certain fish species, lose their compass. The Lachamp excursion of 42,000 years ago, when the field dropped dramatically but then recovered without a full reversal, left signatures in ice cores from Greenland and Antarctica showing elevated cosmic ray flux. Cave records from Europe and the Middle East show corresponding changes in cosmogenic isotope ratios. Some researchers have connected the timing to accelerated extinctions of large mammals in Australia and South America, though the causal chain involves multiple interacting factors and remains an active area of research. The point is not that we are about to experience a Lachamp scale event. The point is that events of this type are normal features of Earth's behavior. They are not catastrophes on geological timescales, but they are not trivial on human timescales either. Now consider the geological records testimony about periods when multiple systems changed simultaneously. The end of the last glacial maximum, roughly 15,000 to 20,000 years ago, represents the closest analog in recent Earth history to the situation we are now entering. As those ice sheets collapsed, massive volumes of meltwater entered the ocean, redistributing planetary mass in ways that directly parallel what we are measuring today from Greenland and Antarctica. The crust freed from the weight of the ice began to rebound, a process that is still continuing and that will continue for thousands of years more. The redistribution of mass affected the moment of inertia and therefore the rotation rate. Sea levels rose by more than 120 meters over roughly 10,000 years, an average rate of more than a centimeter per year, with episodes of much faster rise. The geological record of that deglaciation shows that the redistribution did not produce smooth, gradual changes in sea level or rotation. It produced irregular, stepwise shifts as different ice sheets collapsed in different sequences, as meltwater pulses occurred in episodes rather than continuously, and as the solid Earth responded with its own delays and rebounds. The most dramatic of these meltwater pulses, Meltwater Pulse 1A, approximately 14,500 years ago, raised global sea levels by roughly 14 to 18 meters in a span of roughly 300 to 500 years. The redistribution of that volume of water in that time frame was large enough to leave a detectable signature in rotation models. The volcanic record adds yet another dimension. During periods of rapid deglaciation, volcanic activity tends to increase. The mechanism is pressure release. Ice sheets exert enormous weight on the crust beneath them. When that weight is removed, the crustal pressure drops, and the mantle rock beneath, already near its melting point due to geothermal heat, becomes more likely to melt and rise. Research on Icelandic volcanic history shows elevated eruption rates during and after the last deglaciation, with a lag of centuries between ice removal and volcanic response as the crust adjusted. Monitoring in Iceland, Greenland's peripheral volcanic zones, and West Antarctica has already shown subtle changes in subsurface pressure and seismic activity consistent with the early stages of a deglaciation-driven volcanic response to current ice loss. The picture that emerges from the geological record is not one of catastrophe on human timescales. It is one of interconnected changes, each driving the next, each adding to a cumulative shift that takes centuries to fully express. What the geological record of the last glacial retreat tells us, most directly, is that these mass redistribution events do not produce gradual, predictable, smoothly evolving changes. They produce nonlinear responses, thresholds, surprises, and we are in one now. In research institutions studying Earth's geophysical behavior, there is a type of visualization that has become increasingly common in the last 5 years. It takes the independently measured datasets from multiple monitoring systems: rotation, magnetic field, ice mass, ocean circulation, atmospheric angular momentum, normalizes them to a common scale, and plots them together on the same timeline. The result is what researchers refer to informally as the alignment. And when you see it, the convergence is not subtle. Inner core rotation anomaly data, referenced against the 1990s baseline, a clear departure beginning around 2009 to 2010. The departure strengthens through the mid-2000s. Outer core angular momentum estimates derived from magnetic field change rates, a concurrent shift beginning in roughly the same window, with a slightly different profile reflecting the different coupling time scales between inner and outer core. Surface rotation data. The acceleration begins to emerge clearly from background noise around 2016, with the most extreme values appearing in 2020 through 2022. Greenland ice mass loss rate, plotted against its pre-2000 baseline, a step change increase beginning around 2012, continuing to steepen. South Atlantic anomaly minimum field intensity, tracked since satellite measurements became available, a consistent decline with a steeper gradient emerging in the mid-2000s. Arctic sea ice extent, used as a proxy for the atmospheric circulation changes affecting jet stream behavior. Its sharpest multi-year decline beginning around 2012. Atlantic meridional overturning circulation strength estimates, derived from ocean heat transport proxies and direct measurements, accelerating weakening in the mid-2000s. 7 independent geophysical time series, measured by different instruments, analyzed by different research groups, published in different journals, funded by different agencies, each pursuing its own scientific question, each showing its major departure from the historical baseline in roughly the same decadal window, centered on approximately 2010 to 2020. The probability that 7 independent geophysical systems all departed from their historical baselines within the same decade by coincidence, with no shared physical driver, no common cause, no coupling between them, is not zero, but it is very small. What this convergence suggests is that these systems share a common excitation. Something changed in the coupled Earth system during that window in a way that propagated across multiple layers simultaneously. Whether that something was primarily the inner core changing its rotational behavior, primarily the ice atmosphere system entering a new regime, or primarily a magnetic transition beginning to accelerate, the effect was system-wide. And system-wide changes in Earth's coupled geophysical behavior do not stabilize quickly. The geological record shows that when multiple systems enter a departure phase together, they tend to remain in that departure for decades to centuries before finding a new equilibrium. The equilibrium they find at the end is not identical to the one they left. 3 distinct theoretical frameworks have emerged from the literature to explain the convergence, and understanding them is essential to understanding what comes next. The first is the core-driven model. In this framework, the primary driver is the change in inner core rotation and its effect on outer core circulation. The inner core's apparent behavioral shift from superrotation to matched rotation to possible subrotation transferred angular momentum upward through the layers. The surface acceleration is the delayed echo of that transfer. The prediction from this framework is that the acceleration will continue until the angular momentum transfer is complete, then stabilize or reverse as the system finds a new equilibrium, a process estimated to take decades. The second is the ice-atmosphere coupling model. This framework holds that the dominant driver is the combination of polar ice loss and its cascading effect on atmospheric circulation. Ice loss weakens the temperature gradient between the Arctic and mid-latitudes. That gradient drives the jet stream. A weaker gradient produces a slower, wavier jet stream that redistributes atmospheric angular momentum differently. The surface acceleration in this model is primarily an atmospheric response to an ice-forced circulation change. The prediction is that the acceleration will track the trajectory of Arctic warming, continuing as long as ice loss continues. The third is the electromagnetic coupling model, the most speculative of the 3, but not without physical basis. In this framework, the weakening of the magnetic field, particularly in the South Atlantic region, is changing the electromagnetic coupling between the outer core and the lower mantle. A weaker coupling means less rotational resistance between the 2 layers, allowing the core to transfer angular momentum to the mantle more efficiently. The surface acceleration in this model is a symptom of a magnetic transition, possibly an excursion or the early stages of a full reversal. Each of these models has published support. Each has published critiques. None has been falsified. And crucially, none is mutually exclusive. All 3 could be partially correct. All 3 could be operating simultaneously, with different contributions to the total signal at different time scales. What all 3 share is the recognition that the current situation is not a random fluctuation. There is a physical story being told in the data. The debate is about which chapter you are reading. The atmosphere participates in this story in ways that extend beyond any single model. Earth's atmosphere, a layer of gas with a total mass comparable to that of large mountain ranges, moves constantly. When it moves, it pushes, and its angular momentum couples directly to the rotation of the planet beneath it. This coupling is not theoretical. It is measured directly. When the atmosphere gains angular momentum, typically through the amplification of large-scale wind systems, the solid Earth slows down slightly to conserve the total. When the atmosphere loses angular momentum, the solid Earth speeds up. The dominant signal in this exchange is seasonal. Winter jet streams carry more angular momentum. The Earth responds by rotating slightly slower in boreal winter. The effect is small but measurable at atomic clock precision, on the order of 1 millisecond variation across the year, but there are non-seasonal components that are directly relevant to what we are seeing now. El Niño events are the most significant. During a strong El Niño, trade winds weaken across the tropical Pacific. The atmosphere transfers angular momentum to the ocean, and the coupling from the ocean to the solid Earth produces a detectable change in rotation rate. The 2015 to 2016 El Niño was one of the strongest on record. It coincides closely with the beginning of the surface acceleration trend that researchers had been tracking. El Niño alone cannot explain the magnitude or persistence of the acceleration. The signal has continued well beyond the El Niño's influence and is larger than El Niño alone can account for. But it may have contributed to the initial departure from baseline behavior that the core and ice dynamics then extended and amplified. A shifting jet stream pattern, which had been documented over the past 2 decades and is linked to Arctic warming and ice loss, changes how atmospheric angular momentum distributes across latitudes. The stratospheric polar vortex, when it weakens and disrupts, spills cold air toward the equator in a way that redistributes atmospheric mass and creates a brief but measurable rotational pulse. The atmosphere is not just a complicating factor in the rotation story. It is an integrating factor. It receives signals from ice loss, ocean warming, and core-driven magnetic changes, and it rebroadcasts them as mechanical forces on the crust below. Every year, the atmosphere changes its contribution to rotation. And the atmosphere is changing faster now than at any point in the modern record. The oceans participate as well, through drag, through angular momentum exchange, and through the redistribution of mass as their volume and circulation patterns change. The Atlantic Meridional Overturning Circulation, the great conveyor belt that carries warm surface water northward toward Europe and returns cold, deep water southward, has been weakening. Multiple independent data sets confirm this. Some studies suggest it is now at its weakest point in at least 1,000 years. The rotational implication of a weakened overturning circulation is not straightforward. Different components of the change add and subtract from Earth's rotation in different ways. What is clearer is the thermodynamic side. Warmer ocean water is less dense. A less dense ocean occupies more volume. Sea level rises not just because ice melts, but because the water itself expands. And as the upper ocean warms and the vertical structure changes, the distribution of angular momentum within the ocean column changes, affecting how it couples to the rotation. A warmer ocean also generates more intense storms. A major hurricane is a rotating atmospheric structure containing significant angular momentum. An ocean that generates more intense storms more frequently is an ocean that perturbs the rotation budget more often. All of these signals, core, ice, atmosphere, ocean, magnetic field, are real, independently confirmed, and changing in the same decadal window. The convergence is not a narrative imposed on the data. It is what the data shows when you put it all on the same graph. The question is what it means, and the answer to that question depends on something that science cannot yet determine with confidence. Whether the coupled feedbacks stabilize at a new equilibrium within the next few decades or continue to amplify. A new epoch begins. Whether we are ready or not, there is a concept in complex systems, science called a non-stationary state. A system is stationary when its statistical properties, its mean, its variance, its response to perturbations, remain constant over time. The models calibrated on its historical behavior remain valid. The future, while uncertain, falls within the range the past has established. A system is non-stationary when those properties change. When the mean shifts, when the variance increases, when the historical record becomes a less reliable guide to future behavior, not because the measurement was wrong, but because the thing being measured has fundamentally changed. Earth is now in a non-stationary state. The rotation is anomalous, accelerating beyond any measurement in the modern record. The inner core has shifted its rotational behavior. The outer core's circulation has changed, producing both a rotation signal and a magnetic field signal. The magnetic field has weakened regionally and globally, with a specific anomaly expanding over one of the most populated regions on Earth. The ice sheets are losing mass at rates that were not projected to occur until later in this century under median climate models. The meltwater redistribution is shifting the planet's axis and altering its moment of inertia. The oceans are warming, expanding, and changing their circulation. The atmosphere is responding to all of the above and feeding its own angular momentum changes back into the rotation. Each of these changes is documented. Each has its own research literature. Each is being monitored by separate scientific communities with separate funding streams. What is less common is the attempt to look at all of them together. When researchers have done that, when they have placed the time series of each system on the same graph, normalized to the same scale, the pattern that emerges is not ambiguous. 7 independent geophysical systems all showed their major departures from historical baselines in roughly the same decade. The probability of coincidence is small. The implication of shared causation is large. The changes are coupled. The weakening magnetic field reflects outer core changes that also affect rotation. Ice loss affects both rotation and ocean circulation, which affects the magnetic field's excitation pattern. Atmospheric shifts affect rotation and also affect where precipitation falls, which affects ice accumulation rates. These are not metaphorical connections. They are physical couplings with measurable signatures. The result is a system moving in multiple dimensions simultaneously, where movement in each dimension amplifies movement in the others. This is what the technical literature means by non-stationary. The system is not broken. It is not heading toward catastrophe on any human time scale. It is transforming. And the transformation is further from any historical analog in the instrumental record than at any point in the lives of anyone reading these words. The infrastructure of human civilization was not built to operate across a geophysical transition. It was built to operate in a period of unusual stability. Stable by geological standards, stable by the standards of Earth's long history, it's stable in a way that allowed the assumption of a fixed rotation rate, a predictable magnetic field, stable ice masses, and well-understood ocean circulation patterns to be baked into the design of satellites, power grids, financial systems, and navigation infrastructure. Every one of those assumptions is now being tested, not catastrophically, not all at once, but consistently, measurably, and in a direction that creates increasing pressure on systems built for a different planet. The satellite navigation systems that guide aircraft to within feet of runways in zero visibility are now requiring more frequent updates to Earth orientation parameters. Aviation authorities have already issued technical bulletins acknowledging that increasing anomalies in Earth's geomagnetic and rotational behavior require more frequent navigation database updates. The power grids that use time synchronization to balance electrical loads across interconnected systems spanning thousands of miles are operating in a timekeeping environment that their protective systems were not calibrated for. Grid operators in Europe and North America have both published technical analyses acknowledging that existing protective systems are adequate for the current level of anomaly, but would require recalibration if the anomaly grew significantly. The financial systems that execute millions of trades per second against timestamps accurate to the microsecond are facing the prospect of a timekeeping environment that their compliance frameworks were not designed for. High-frequency trading systems, clearing platforms, and regulatory reporting requirements were all built on the assumption of stable, forward-moving time. The global positioning systems that guide ships through narrow straits at night, that tell self-driving vehicles where they are to within centimeters, that allow the construction of tunnels from both ends simultaneously, all depend on Earth rotating at a rate that the correction models have accounted for. When the planet accelerates in unexpected ways, those models lag behind reality. None of these are failures. Yet, they are strains. They are the early manifestations of a system operating outside the range it was designed for. A system whose margins are being consumed by a planet that is behaving in ways its designers did not anticipate. Here is what the scientific community knows with confidence. Earth is rotating faster than it has in 50 years of precise measurement. Multiple geophysical systems have departed from their historical baselines in the same decade. The causes are partially understood and partially still being investigated. The rate of change across multiple systems is faster now than at any point in the instrumental record. Here is what the scientific community does not yet know. Whether the current acceleration is a transient fluctuation that will naturally reverse, or the beginning of a sustained shift to a new rotational regime. Whether the inner core's behavioral change is a genuine reversal or a different type of structural shift. Whether the South Atlantic anomaly represents the early stages of a geomagnetic excursion or a full reversal, or simply a regional fluctuation within the normal variability of the geodynamo. Both scientific perspectives on the current situation, the one that sees a transient fluctuation in overlapping cycles, and the one that sees a structural shift driven by non-cyclical forcing, have valid points. Neither has the data to decisively win the argument, and the honest answer from researchers closest to the data is that the range of possible futures is wider than it was a decade ago. More monitoring has produced more evidence of change. Better models have produced better resolution of the mechanisms, and better resolution has revealed how tightly coupled the systems are, which means how much a change in one can drive changes in others. What the geological record tells us about periods of simultaneous multi-system change is this: the transition period is the dangerous part, not the new state at the end. Life has navigated new states repeatedly across 4 billion years. The journey between states. During that journey, the planet is in a configuration where small additional forces can produce large responses, where thresholds are crossed unexpectedly, where behaviors calibrated to yesterday's conditions produce different outcomes today. That transition is not coming. It is already underway. The systems that would be most affected are the ones with the least redundancy, the tightest timing requirements, and the fewest built-in margins for a planet that behaves unusually. The engineers and scientists responsible for those systems know this. They are watching. They are adapting. They are running the calculations that most of the world does not know are being run. What they cannot yet tell us, what no model can currently answer, is how fast the transition will proceed. Whether the coupled feedbacks will find a new equilibrium within a generation or continue to amplify across a century, whether the magnetic field will stabilize, excurse, or reverse, whether the inner core has settled into a new rotational regime or is still in motion. The answer to those questions is being written right now. In the data streaming from the swarm satellites mapping the magnetic field. In the distance between 2 GRACE spacecraft measuring the gravitational field. In the signals from radio telescopes pointed at distant quasars to measure Earth's orientation in space. In the travel times of seismic waves from earthquakes at the same fault locations recorded at the same stations decades apart. In the rotation of a planet you are standing on. In the movement of ice you cannot see. In the churning of iron 1,800 miles below your feet. The instruments are running. The data is coming in. And what it shows is a planet in transformation, not broken, not dying, not heading toward human extinction, but moving into a new geophysical regime with consequences for the infrastructure and assumptions of a civilization built during an unusual period of calm. Human civilization was built in the calm. The calm is ending. What comes next depends on how fast, how coupled, and how far outside the range of the last 10,000 years the planet is willing to go. We do not yet know the answer. We are living through the question. The Earth is not the same planet it was 50 years ago. Not dramatically, not in ways you can feel in your daily life, but measurably, consistently, in multiple systems simultaneously, in a direction that researchers are working urgently to understand. And the most important sentence in this entire documentary is also the simplest one. We are watching. For the first time in human history, we have instruments precise enough to detect what the planet is doing in real time. We have a global network of scientists sharing data across borders and disciplines to build a picture no single institution could assemble alone. We have models sophisticated enough to identify what we do not yet understand. That is not a reason for panic. It is a reason for attention. The planet is speaking. The question is whether we are listening carefully enough to understand what it is saying before what it is saying becomes something we can no longer prepare for. The instruments are running. The data is coming in. We are watching.